Here we are at the end of week 11. Today we're going to see ways on repeating code that can possibly be infinite. A couple days ago we talked about for loops, which was a way of iterating through finite things. Sometimes it's necessary to do things infinitely or up to a certain point that you're not sure about. While loops are good for that. So today we're going to do a couple examples on while loops. I'm actually not going to use the notebook, the lesson number 16. I'm actually just going to open up some brand new scratch pads and just kind of work from there. And then you can use lesson 16 as a supplementary thing if you want. But yeah, first we'll start off with a couple examples on while loops, and then we'll move on to something a little conceptual. It's called a finite state machine. We'll talk about this towards the later half of class. A finite state machine is a little conceptual, but it's a way of representing kind of infinite loops. For example, you can think of like maybe you're at a subway, and the subway has a gate where in order to unlock the gate, you'd have to put a coin in. And when you put a coin in, it should unlock it, meaning that you can push it and it'll rotate. So this is kind of like a finite state machine where you can think of it as a program that runs infinitely and it's listening for input. Depending on the input, the state will change from locked or unlocked. We'll be talking about this later. It's going to be a pretty cool application, actually. This is going to be some useful stuff because some hardware runs on a finite state machine concept. For example, if you've ever worked with the Arduinos, if you ever worked with this microcontroller board, it is a finite state machine that you can upload code to, and the code can control certain aspects of here. There's some pins, and you can connect the pins to hardware and control it. Pretty much this is a finite state machine. You can think of it as it's running in an infinite while loop and constantly listening or waiting to do something. Okay. So finite state machines. Well, this is an application of while loops. We'll talk about this later. Let's start off with a small intro on while loops. A long time ago, we did a sneak peek into this concept. All the way back in week 5, on week 5 on Thursday, we talked about functions and gave a sneak peek by applying these functions into an infinite while loop. The sneak peek here was a very small roulette game. In the examples directory, you might remember we created a small roulette game, which is really just a guessing game. Here are a couple functions, helper functions, that are meant to help simulate rounds of a roulette game. This function, play round, simulates a single round of roulette. And you might remember we wrote a infinite while loop down here, not infinite loop. Let me play this real quick. I'll play this first cell to bring it in. And then this next cell is looping the helper function over and over again until the user runs out of money. So if you understand this from a long time ago, then today should be pretty chill. We're talking about repeating code, but we're not sure when to stop repeating the code. In this case, the program starts off by asking for a bankroll. It's asking the user to type in a number that we'll buy in with. I'll buy in with 200, meaning that I have $200, and then the while loop is like an if statement. There's a condition here that defines when to run the body of the loop. Upon initialization, the condition is true because we typed in a number above 0, meaning that we entered the while loop and now we are simulating the round. Actually, we didn't simulate a round yet. We need to input 2 numbers. I'll input 2 numbers here. How much are you betting? $10. And then I'll go ahead and bet on the number 15, my birthday. And then when I press enter, we're going to simulate a round. This play round is a helper function defined above here. The point of this play round function is to kind of just spin the wheel and return a positive profit or a negative profit. So I'm going to go ahead and press enter here, which will simulate the round. There it is, spinning the wheel. And then ball landed on 6. I lost, and the play round function returned a negative profit, meaning our bankroll is now a little less. This is an example of a while loop where we're not sure it's going to end yet. It can possibly be infinite. In this case, it'll be infinite if we maybe keep winning. But if I were to go all in here, go bet 190, this is the rest of the money, rest of the bankroll, and then just put it on some number again. I'll put it on 15 again. Press enter. It's going to simulate another round. There it is, spinning. And ball landed on 20. I lost all the money there. So the while loop quit because bankroll was 0, meaning that this is false. And when the condition is false, we will finally terminate the loop. If you're familiar with all of this, then it's going to be a pretty chill lesson. We're going to break this while loop down a bit and simplify this scenario. This is really just a glorified guessing game. Let's go ahead and rewrite this, build it from the ground up, and kind of simplify it a bit. Okay, let me make a new notebook here. I'll make a new notebook, call it guessing game. This is just going to be a simplified version of roulette. Okay, here's a notebook called guessing game. Let's build this from the ground up. Sometimes it's necessary to loop things infinitely. In this case, you can hard code a infinite while loop. Here I put a true here. This is a literal, meaning that I'm hard coding this to always run. For a glorified guessing game, we typically ask the user, hey, guess a number. So I'll go ahead and take input from the user and prompt them to enter a number. Enter a number. So this is an infinite while loop where the user can type in numbers over and over again. I'll press enter here. Press play. Press play. The while loop is true because I hard-coded a true condition here. So we're going to enter the loop and type in something. So I type in like 5, enter. When I press enter, it loops back up to the condition and checks if this is still true. Yes, this is still true. And I can type in more numbers. See, typing in more numbers, this is an infinite while loop. If anything, if we want to make this a guessing game, we need to give it a reason to quit. So typically with guessing games, there's some magic number that you must guess. So I'm going to go ahead and pretend to generate a random number. Like let's say answer is what we want them to guess. In this case, I'm just going to hard code some number here, like 2025. Just keep it small. Oh, also, I forgot to quit this loop. This cell is still running because of this asterisk. So I'm gonna quit this with the stop button. So stop. Yeah, don't forget that in infinite while loops, we have to press stop to quit it. Okay. When the user enters in a number, it might be useful to store this in a variable. This way we can compare it to the generated number. So I'm gonna go ahead and store it into a variable called user input, meaning that whatever we type in will get stored into this variable. If anything, it might be useful to convert this value to an integer. The reason why is because we're planning on comparing the user input with the answer. And by default, the input function returns a string. So since it returns a string, we have to convert it to an integer in order to properly compare it with this number here. Cool, so we'll grab the user input, and then now we can write a couple branches to determine if it matches. I'll say if user input is equal, two equal sign because we need to compare for equality. If the user input equals the answer, then maybe we could say correct. And then else we could just say incorrect, meaning they didn't guess it right. Okay, let me go ahead and play this. Press play. Okay, let's trace through this program. We are inside the while loop because the condition is true, waiting for a number. I'll type in like 5, and then enter. It says incorrect because this first branch isn't true. Type in more numbers. These are, oh, I typed in the correct number here on accident. And it printed correct because this is true. Type in more incorrect numbers. These are still incorrect. So the people see what we're doing here. We're looping this branch over and over again. Sometimes it might be necessary to break out of a program. Currently, there's no way to quit this program without interrupting it. Meaning we would have to press the stop button here to terminate the loop. This asterisk means it's still running. So I'll press this. There it is. Now we stopped. We interrupted the program. And let's go ahead and implement functionality where this condition is no longer hard-coded. There's a couple different ways we can do this. One way we can think about it is by representing a Boolean variable that controls the loop. You can imagine a Boolean variable called game over. Game is over. A Boolean variable is true or false. I'm going to initialize it to false because when we start the game is not over. We can use this Boolean variable to control the loop, where we should keep playing the game while the game is not over. That's what this condition is saying. Upon initialization, this is true because false is equal to false. So at some point, we need to revert the Boolean. Probably when we get it correct. When the answer is correct, we can set the Boolean variable to true. So when we loop back up to the condition, this will become false, meaning it'll finally terminate the function. So I'll press play here again. Press play, enter in a number. Let's enter 5, incorrect, enter number 10. 10 is incorrect. And then when I finally type in 25, the correct number, it'll terminate the loop. So I typed in 25, meaning that this branch became true. So we printed correct, and then we reverted the Boolean, negated it, meaning that the condition becomes false. True is not equal to false. So this terminates the loop, and it'll bring us to the end of the program right here. The end of the program here is just a print statement that says congratulations. End of game. Let me play this one more time. So I'll press play here and put some incorrect numbers. We're inside the loop, and then finally type in 25, and there it is, correct. And end of program. So yeah, we just implemented a condition that allows the loop to terminate. So we no longer have to interrupt the program anymore. People cool with this? This is kind of like a simplified version of the roulette that we wrote. All the way back in week 5, we did this roulette game over here. And here's a simplified version. If anything, I'm kind of I don't really like this hard-coded number, this 25. Maybe you could randomly generate it. I'll go ahead and randomly generate it. There's a function called random, and I mean not function. This is it's like a library of classes, and you can use the random dot. Let me look at the documentation. Random Python library. I'm trying to find the class function that generates a random integer. Random, I think it's called randint. Okay. Here's a function that generates a random number between 2 bounds. So I'll go ahead and use this function. Random.randint within the bounds of let's just keep it simple, like 0 to 100. Or no, I'll keep it as 10, because 0 to 100 is gonna be a very long game. Here we are. We generate a random number from 0 to 10, and let me give a hint. I'll put in the prompt. Enter a number between 0 and 10. Does it include 0 and 10? Let me check the documentation. Yeah, it includes 0 and 10 because of these less than equals. Okay. Cool. Let me play this one more time. Press play. There we go. Enter a number between 0 and 10. Let's go 5. Incorrect. Let's guess another number. Let's go 6, 7, and 7 ended up being the randomly generated number. Okay. People cool with this so far? If you wanted to insert more functionality, you could add more branches. It would be a good exercise, actually. If folks want to try this on their own time, I would recommend inserting branches to give the user some hints. For example, if they got the number too low, maybe the branches should say, too low or too high. So yeah, I'd recommend adding a couple more branches. It'll be good exercise. Okay. Any questions about this so far? Okay. That's pretty much what a while loop is good for. Looping code that can possibly be infinite. While loops, every for loop can be written in a while loop, by the way. So I'm gonna make another notebook and kind of show the symmetry between them. Let me make a new notebook here. This notebook is going to be showing the symmetry between for loops and while loops. So I'll name this for versus while. Okay, once again, for folks who just joined, I am not using the lesson for today. The lesson is number 16. You can take a look at it if you want. It's pretty much doing the same exact thing we're doing. Feel free to look at it for supplementary stuff. But yeah, for today, I'm just working with plain notebooks. Okay, let's demonstrate the differences between for loops and while loops, or show the similarities. Back in the lesson on for loops, you might remember we were looping through lists in the very first cell. So I'm going to go ahead and copy this from the for loops and paste it over here in this blank notebook. Make a quick modification. This is stuff from a couple weeks ago, a couple days ago, where we showed for loops that iterates through a sequence. You might remember that you can represent this for loop in another way by going through a range of numbers instead. For example, if we were to write a for loop that goes through number in a range where the range is here 3. People remember what this range 3 is doing. Range 3 is a sequence that represents 0, 1, and 2. Just to prove it real quick, if you were to look at what this evaluates to, if it's converted to a list, this evaluates to a list of 0, 1, 2, meaning that each number here is 0, and then 1, and then 2. Okay, this 3 is hard-coded. It might be better to represent it as the length of animals. This will give us a more general number 3 in this case. So we could use this number to index positions in a list. The number is 0, 1, and 2, so we can access the element at 0, element at 1, and 2. Here we go, print animals, and let me print the equal signs as well. Okay, there we go. Let's test it. And we get the same exact behavior as up here. So these are kind of two different ways on doing a for loop. This second way can be written as a while loop. You can represent a while loop that goes from 0 to the end of the range. So let's do that. Using the same exact list, we can represent this for loop by kind of refactoring it into a while loop. This for loop is really starting at 0 and going to 2. That's what it's doing. We can do the same thing by initializing a number to 0 and then writing a while loop that performs code until it reaches a certain range, length I mean. The condition here would be, while the number is less than the length of animals. This condition is saying while the number is less than 3, then do something. In this case, just go ahead and access the element. I'm going to access the element by indexing the number into the list. And go ahead and print the equal sign as well. Okay, a very quick thing that might happen. It's whenever we're designing while loops, it's possible to run into logical errors where the loop will never end. If I were to play this cell right now, it's never going to end. I'll press play. So here it is. I press play. There is this asterisk meaning that the cell is still running. And you can scroll very far down. There's probably like 1 million lines in the notebook now. So this is being infinitely printed. It's never stopping. You can scroll down as far as you want. It's never gonna stop. There is a interrupt button here. This stop button is pulling the plug on the program. So I just pulled the plug on the program and it terminated. This is a infinite while loop because the condition is always true. 0 is always less than 3. So we need to increase this number within every iteration. Every iteration number is going to increase by 1, meaning that on the very last iteration, this is going to become false. When number becomes 3, 3 is no longer less than 3, so this will become false at the last iteration. Press play, and there we go. We get the same exact behavior as up here. Let me put it side by side. Here's the for loop version, and this is the while loop version. Okay. People getting a sense on how nearly every for loop can be represented as a while loop? Okay. A couple of days ago, we also talked about simulating compound interest. Back in the loops lesson, there was a cell where we simulated compound interest over a certain amount of years. Here it is. I'm gonna go ahead and copy this into the notebook, into the empty notebook. Not empty, the new one. We saw this for loop a couple days ago. It's simulating a savings account getting bigger and bigger, where every year the account accumulates a certain amount of interest. Let me keep it small. Let me go from 2025 all the way to 2030, just so I don't have a lot of output in the down here. So I'll press play. This for loop is saying for all the years between 2025 and 2030, we're gonna accumulate the interest, add it on to our savings account, and just print out what's happening. So this is a for loop that is guaranteed to end in 5 iterations. Sometimes it might be necessary to write this into a while loop. For example, what if we wanted to know when we doubled our money for some reason? Basically, I'm trying to say, here, let's actually just refactor this right now. So I'm gonna make this into a while loop. Let me reinitialize these variables and start the while loop. The while loop should represent a year going from 2025 all the way to 2030, meaning that there is a year variable that is initialized to 2025. That's what this for loop is doing. It starts here at 2025 and then enters in a loop where it says while the number is less than the upper bound, then we're going to accumulate the interest. So we'll accumulate the interest. Let me copy and paste this over here. Copy, paste, and we can go ahead and get this print statement as well. Okay, here we are. We start at year 2025. We say while the year is less than 2030, accumulate the interest and print it. Let's play and see what happens. We have an infinite while loop that never stops. Once again, there is this asterisk, so the cell is still running. You can scroll down really far, but it's going to be really hard to reach the bottom. Hopefully people see the logical error that's happening here. We meant to have the loop stop at 2030, but currently the year always stays the same. 2025 is always less than 2030, so this is never going to end. Let me quit the notebook. Let me stop this cell real quick. It's lagging out my notebook. So let me stop this cell. There it is. And we need to update year for every iteration. So inside the while loop, I'll go ahead and increment the year by 1, meaning that the last iteration will make this condition false. And we'll only do 5 years. Okay, people cool with this so far? All we did was represent this for loop into a while loop. So if you're able to translate it, this will make more sense. Sometimes it's necessary to represent the condition to something where you're not sure. What if we wanted to find out how long it takes to double our money? In this case, we'd have to change the condition where it'll represent keep doing the computation until we reach our goal, or keep doing the computation while we're underneath the goal. That's what I'm saying. Assuming, let's say our goal is 2 times our money. So I'll create a new variable here. I'll call it goal or target. And I'll set it equal to 2 times the savings account. If we wanted to figure out how long it takes to double our money, we would just have to modify this condition to say while we're underneath our target. While we're underneath our target, keep accumulating. So let's test it. Press play, and here it is. We keep looping, and it turns out we double our money in 2045. Cool. People cool with this so far. If you wanted to figure out when you'd reach another number, like let's say, for example, target is $1 million for some reason. Is this $1 million? Let me see. 1, 2, 3. 1, 2, 3. Cool. I'm just changing the target to 1 million. I'm curious how long it takes. If we start with 2K. Now let's press play again. Press play. And here we go. It looks like we'll reach $1 million by 2210. So yeah, couple hundred years. Okay, let me scroll back up to the code. I'm curious, what about for 1 billion? So I add 3 more zeros here. How long is it going to take us to reach $1 billion? Let's see. Press play. And it looks like by 2417. Interesting. I thought it would be longer, actually. Okay, it only takes like 400 years. Interesting. Let me sanity check this. Yeah, I guess that makes sense. Yeah, that makes sense. If you wanted to sanity check it, you could look at the closed form solution for compound interest. The closed form solution is defined by this formula here, where you can plug in your variables and figure out how long it will take to reach 1 million. So you could use this closed form. Once again, this is a little tangent, but this closed form solution comes from simulating addition over and over again until it reaches a certain thing. It's called taking the limit of an equation. Anyways, hopefully people are seeing the use cases for while loops. It lets us repeat code that we're not sure how many times it's going to go for. Okay, any questions about this compound interest thing? Compound interest is actually a little more complicated than this, by the way. It's not really straightforward as multiplying. Basically, the interest rate is divided by some amount of time, and then you're actually accumulating differently. But yeah, this was just to simplify the calculations a bit. Any questions about this so far? Okay, we're almost done for today. Once again, we're just introducing the while loop. There is no associated lab with this, but it's useful stuff to know. The lesson here, lesson 16, feel free to take a look at this. We already pretty much did this stuff. It's pretty much going through the guessing game and re-explaining things, and also putting things into functions. So I would recommend looking through this if you're still having a bit of trouble on while loops. Okay, hopefully that makes sense so far. Let's move on to one more topic and we'll be done for today. This last topic is a little conceptual, but it's very applicable to a lot of different topics. It's called a finite state machine, which is a mathematical model of computation. A lot of software can be represented as a finite state machine. A lot of machines can be as well, especially in robotics. Here's a simple example that we showed in the beginning of class. Imagine you're at a subway and there is this gate that has a couple different states. The state is locked or unlocked. If it's locked, we have a couple options, a couple branches that can be performed, like pushing. If you push a locked, If you push a locked gate, it's going to remain locked. If you put a coin in it, it should change the state and put it into unlocked. And when we're in the unlocked state, there's two other branches here. In this case, the branches are defined as, if we're adding a coin, then it remains unlocked. So it looks like there's some money being wasted over here. In this, meaning that if it's unlocked, you can put more coins in, and it'll just remain unlocked. But yeah, that's just to keep the example easier to understand. So here are a table that represents the tree. You can really think of this as a decision tree, a infinite decision tree actually. Back a couple weeks ago when we talked about if statements, these were kind of not really infinite, meaning that the program will end at some point. The program would make some decisions, and when it reaches the leaf, that would be the end of the program. But sometimes it's necessary to design software that has infinite decision trees. Not infinite decision trees, more like it's connected and cyclic. Cyclic meaning there's some cycles in there. So that's the finite state machine concept here. Let's go ahead and simulate this gate in using a while loop. Okay. Let me see, where should I do this in? I guess I'll just make another example. I'm going to make another notebook here. In the examples directory, I'll make another notebook. Let me call it, what should I call it? I'll call it finite state machine. Finite state machine. And we're going to represent this state diagram here using a while loop. Put it side by side. Okay. Okay. Let's see. Hopefully people can read this. Let's go ahead and design this and talk about some future applications with this loop. You can think of this as an infinite loop. Let me open up this image actually. Actually, I'll leave both of it here. Hopefully people can read it. You can see by the diagram that upon initialization, it's locked. I'll open up the thing right here. So yeah, when you go to the gate, it's default locked. So it might be a good idea to represent this variable. I'm gonna represent these circles as the states. So I'll in the notebook, I'll create a variable state. This is really just going to be a string that represents what state the gate is in. And in this case, it's gonna be locked. You don't have to use a string. You can use a Boolean if you want, but I'm gonna use a string to be a little more general. Okay, so the state starts at locked. And now, imagine an infinite while loop. Imagine the gate is constantly listening, meaning it's waiting for input. It's waiting for a customer to come by and either put a coin in or push. So this is the infinite while loop that I'm talking about. It's constantly listening. So I'm gonna hard code an infinite while loop here. While true, this is the literal. It's gonna force the body to always happen. For now, I'm just gonna do a print statement that kind of displays the state. The state, machine state is, and I'm gonna interpolate the variable here as an f string. Okay, machine state is locked. So this is just an infinite while loop. I'm gonna play it real quick just to make sure there's no syntax errors. So I press play. It's an infinite while loop that's always printing locked. There's gonna be a million lines, so I'm gonna quickly stop it. So quickly stop it because it's infinite. There it is, I stopped it. So here we go. We just simulated an infinite while loop that's listening. Actually, it's not listening. It's just doing something. If anything, we could put an interruptive thing here that kind of listens for input. Like there's this function here called input that kind of lets the user type something. So I'm just gonna prompt the user to type something like enter a command, where the command can either be push or coin. Push or coin. Okay. Let me press play. Okay. Machine state is locked. We are waiting for input. So I'll type something. I'll type in like push. When we push it, it should stay locked. Yeah, this makes sense because we didn't put a coin in. We could keep pushing and the machine state still stays locked because we need to implement functionality where if we put in a coin, it should be unlocked. You know what I mean? Type in coin and enter, the machine state should say unlocked, but we need to implement functionality for that. So this function does return a string, and it might be useful to store it into some variable. I'll store into a string variable called action. This is kind of a good name to represent this. Oh, also let me stop this cell. It's still looping. Let me stop this cell. There it is. Interrupted the program. Let me clear this output actually. Clear. Okay. So we stored the input into an action. This action can either be push or coin. And based off of that action, we can change the state. If the action was push, the state will remain the same. So this might look a little tricky, but I'm going to end up doing a nested decision tree. And it will look a little weird, but hopefully people can read what's going on. The nested decision tree here is we have two different states. And beneath those two different states, there are two different branches, push or coin. So hopefully people kind of seeing the nesting that's happening here. The nesting, I'm talking about like this right here. You can, these are pretty much the two same diagrams. It's just that the right one is cyclic. So same thing. The internal nodes here would represent locked or unlocked, and then these other leaf nodes would represent push or coin. So I'm gonna use some nesting to represent this, where if the state is locked, then we're gonna do something. It's gonna be either push or coin. So this is gonna be nested. If the action is equal to push, then the state shall remain the same because we never put money in it. So it might look redundant, but I'm gonna say state becomes locked. I know it looks redundant. You actually don't need to do this, but it kind of makes things a little, it completes a diagram. So push, it'll lock. It remains locked. If the action is coin, then the state should change. It should change to unlocked. Okay, people see the nesting that's happening here. I'm representing the locked state where you can push or put a coin. Okay, as for the other branch, the outer branch, there is another state for unlocked. So hopefully people see the nesting here. If the state is unlocked, then this is a different subtree, where if the action was push, if we push an unlocked gate, it should go back to locked, because this diagram is representing this gate here. It should really only let one person in. So by pushing it, it's going to lock it. So state is equal to locked. Okay. I also realized that this might seem weird because of all these equal signs. By now, hopefully people know the difference between double equals and single. Double equals is comparing for equality, and the single equals is for reassigning values to a variable. Okay, and then finally the action. What happens if we put more coins in? What should happen if we put a coin when it's unlocked? Well, based off this diagram, it's keeping things simple. So it's saying if you put a coin in, nothing really happens. It should remain unlocked. So I'm gonna put in a statement here. State remains unlocked, meaning you kind of wasted your money. Okay, let's go ahead and press play so people see what's going on. Okay, here we go. I press play. We are inside the loop, and the state is locked because that's the entry point. And now the machine is waiting for input. So let's say I didn't pay and I tried to push. So I'll type in push. The machine still stays locked. We can keep pushing and it's always locked. But when we finally put in a coin, enter, oh, it still remains locked. Okay, so let's see what happened here. I typed in coin and it should have unlocked it. So narrowing down on this branch, the state was locked. We typed in coin. Oh, I have a typo here. Basically, it is case sensitive, and here I was typing in all lowercase. And let me change some lower cases here. I'm gonna use lower cases for the action. Okay, there we go. That should fix it. Let me go ahead and, where's my P button? Here it is. Let me restart this. So I'll press stop because the infinite loop. Press stop, and then let's rerun the program. Okay, let's test it again. So push. Okay, it's locked, and let me put a coin in. So coin, enter, and there you go. Machine is unlocked. So we're inside of this state now, and if we put in more coins, then we wasted our money because the machine state is still unlocked. So put in more coin, the machine state is still unlocked. And finally, when we push, it'll bring us outside of the locked state, unlocked state, and the machine state will be locked, meaning that the next person will have to pay. So this is an infinite while loop, by the way. It's never actually going to stop. This program will never stop unless we pull the plug on it. So I'm actually gonna pull the plug on it by pressing this stop button. Hopefully people are seeing the applications of finite state machines. Sometimes it's necessary to design programs or software that run infinitely. So that's an example here. If you've ever worked with Arduino or some sort of microcontroller, Arduino Unos, this is some pretty fun stuff actually. I teach a class on this. It's called CIS-15, where you're pretty much using a board and programming it. I think you can program this board with C, C++, and I think you can use Python on this. I forget. But this board, you would upload code on it that represents a finite state machine, meaning that it's running in a constant loop and kind of listening and doing something constantly. So yeah, this is some pretty useful applications. Okay, that's pretty much it for while loops. There's no lab associated with this, but it's some useful stuff. Good old while loops. Okay, let's summarize what we did today. And we're done. We talked about while loops, which is a way of repeating code that we're not sure how many times to repeat. This whole week we talked about loops. Next week we're gonna do some more advanced things. This week all we really did was access elements, but next week we'll do some algorithms that create things. So yeah, stick around for next week's stuff. There's gonna be some pretty cool assignments coming out. There's a assignment called MLB players. I'll introduce this next week. It's going to involve a bit of data analysis, meaning that we're going to end up looping through large amounts of data and calculating things from it. Looping algorithms is really useful stuff because you can, it's the basics of data science, where you can analyze a bunch of data and predict things based off of it. So yeah, stick around next week. Looping algorithms. Okay, that's it for today, folks. Thank you and have a great night.